start recording, and I think we're rolling. Okay, audio is recording, and all right. So we are. Oh my god, I'm so sorry. I'm really tired right now. It's like 10:50 right now, and I'm recording a lecture. But we are moving on to relative motion. Now you guys should have covered, I believe, free fall in Mr. M's class, and what it looks like a very short, brief lesson is that free fall is basically the idea that an object is only influenced by force of gravity, right? That's how you, for Earth in this case, our gravitational acceleration is negative 9.8 meters per second. Now, when I said the negative is referring to the direction, which is basically, in this case, like where I'm sitting right now, it's pointing towards the center of the Earth, right? But for another person on the other side of the globe, it could be pointing up, right? So it really depends on how you look at it. But one thing's for sure, the magnitude is 9.8 meters per second squared, right? So now that we got that out of the way, we're going to cruise on towards the idea of relative motions, right? And actually proposed, well, I didn't propose it, but my teacher, Mr. E, had this warm up right here where we have obviously four objects. We have Bill on the bicycle, a runner, Amy, and Carlos, right? Now, Amy, Bill, and Carlos are watching the runner, right? So you can see here that Amy is staying still watching the runner. Bill is watching the runner while he's biking, and Carlos is watching the runner while he's driving a car, right? You can obviously see here that both Amy, Bill, and Carlos. I just realized that almost turned into like uh, uh Angela, Blake, and Carlos from the AP Physics review. But that enough of that. You can see here that both Amy, Bill, and Carlos are traveling at different velocities, right? And you can see how, in their point of view, they observe the runner's motion differently, right? And the reason why is that it's because of their velocity that they're traveling at, right? For Amy, because she's standing still, she is watching Bill run from point A to point B at 5 meters per second, right? But for in Bill's mind, he didn't he doesn't see the runner overtaking him at all, right? Like it is almost as if, and this is a perfect example that I always share. Imagine you're a runner in a sport or marathon, right? And you're competing against other runners, right? It is clear that you and the runners are running fast, right? It's pretty self-explanatory. But in relationship to everybody else, you can see that there are some runners that are just a tiny bit faster or a tiny bit slower than you, right? And it's because of this tiny difference in the amount of how fast you're going is the concept of relative motion, right? For Bill and the runner, because they're going at the same speed in the same direction, right? It's almost as if Bill and runner were never moving at all, right? It's almost as if they're just moving together in the same direction, right? But for Carlos, in this case, Carlos is driving a 15 meters per second car, right? So he's obviously faster than runner, but how much, right? And that's the idea where we're going to go towards, formulas dealing with, the same concept that we've been dealing with: displacement, velocity, and how we get to determine how fast, how small, and we're just basically measuring that difference relative to us, right? And that's actually where we're going to start right now. Is that the basic idea of a displacement, right? Displacement is equal to the final position minus the initial position. But here's the deal with relative motion. What are you talking about, right? Because relative motion is the idea that you're focusing on the motion of an object in relation to another object, right? And that's why you can see here that when you see an X and BA, what that note subscript mean is that this is the position of object B in relationship to A, right? So that's the same idea as to respecting uh, the runner's motion in Carlos, right? if I were to, notate the change of velocity, I would notate it as the change of velocity of Carlos in relationship to the runner, right? Right? And it's because of that we get this formula. Right? Now, the G basically stands for ground, since we just assume that the motion that we're talking about is relationship to the ground. If I say that a car is driving at let's say 40 miles per second, 40 miles per hour, right? I'm not wrong. It is, right? Like if a car is actually traveling 40 miles per hour, what I'm stating there is that that is the velocity of that car in relationship to the ground, right? Because remember, the ground isn't moving, right? Like if you don't see the ground just shift or go right or left at a certain speed. No, it stays firmly still, right? And that's why the speed of a car could be understand as the speed of a car in relationship to the ground, right? Because the ground isn't moving, right? And but in the case of Carlos and the runner, you can see here that for Carlos, when he's driving the car 15 miles per second, what he sees the runner doing is that the runner is trying to catch up to Carlos, right? That's the thing. But what Carlos is seeing is that the car or the runner is 10 miles per second slower than the 15 miles per second, right? And vice versa for the runner. For the runner clearly sees that Carlos is driving his car 15 miles per second. No, not 15 miles per second, sorry. The runner, who is running at 5 meters per second, obviously sees the car going fast. But how much? By 10 meters per second, right? Even though we, as the observer, see that the car is going 15 meters per second, for in the perspective of the runner, right, he sees it as 10 meters per second, right? And it's because of this difference that we got the displacement formula based on, in relationship to other stuff, and the velocity, right? There should be change of velocity, but that idea of the difference in relationship to certain objects, between two objects in this case, is what the basis or the foundation behind relative motions, right? And basically, in the order to properly define the displacement between two things, you need a third. Third acts as an anchor, in this case, the ground, right? And that's one of the reasons why a displacement, right? We define displacement as, again, it's x final minus x initial, right? But it was also this idea that we are giving ourselves it's not necessarily an origin, but like a frame as to where, like, the bases are covered, right? So, and I know that I can't really necessarily, like, show the displacement of these things, but let's say, like, just for the sake, there are two runners, right? One runner, they both start at 0, right? In relationship to the ground. You see how I said to the relationship to the ground? They start at a position of 0 meters, right? And, like, over a period of time, we can see that, now runner A's new displacement, right? Runner A's new displacement is 20 meters per second, right? And for runner B, his displacement is 10 meters per second, right? And it is because of this difference, right? Runner B covered 10 meters, or has a displacement of 10 meters from where he started, right? In comparison to A had a 20 meter displacement displacement, right? From where he started, right? And basically what I'm trying to tell you is that runner A is 10 more meters ahead than runner B. How did I get that 10 meters? Well, the displacement of B, well, in this case A, relative to B is basically the position of A relative to the ground, right? And the position that I'm referring to is where they are after a certain period of time. In this case, it is the 20 meters, right? So follow the mouse. So the displacement of x, the change in position of A, not B. I know it says B here, but really you can just switch it around. But the displacement of x, the displacement of position of A relative to B, right? So the displacement of runner A in relationship to B is equal to the position of the runner A to the ground, which is 20 meters, minus the position of runner B to the ground, right? Which is 10 meters, right? So 20 minus 10 is 10 meters. And this makes sense, right? This tells us why, or actually tells us how much their displacements are, right? What that basically tells us is that runner A is 10 meters, what's that? 10 meters greater than well, not greater, but like 10 meters ahead. There you go, ahead of runner B. While in runner B's perspective, he is 10 meters behind, right? And that goes for speed also. You can see here that back into this idea, well, it's a model. You can see here that from Amy's perspective, they're all traveling at their normal speed, right? Because remember, we said that velocity. Let me go back. We said that the change in velocity, right? The velocity of B, of an object B relative to A, is equal to the velocity of B relative to the ground minus the velocity of A relative to the ground, right? And that's something that we see here. What if I said, what is the velocity of the runner relative to Amy, right? Well, what's the velocity of the runner, right, relative to the ground? It is 5 meters per second, right? Because the runner is running at 5 meters per second, but the ground isn't moving at all, right? So by that logic, then the runner has to move 5 meters per second. But for Amy, she's not moving at all. It's almost as if Amy is the ground, but the human part is like it's like a protruding like surface of the ground, right? But still, it's the same idea, right? Amy's speed, right, relative to the ground is 0. She's not moving anywhere, right? So by that definition, 5 meters per second minus 0 meters per second is 5 meters per second. And what that basically means is that relative, right, in respect to where Amy is and how fast Amy's traveling, runner B, runner in general, is traveling at 5 meters per second, right? Let's do another one. Let's do the runner in relation to Carlos, right? And because this is like the idea. So the velocity of the runner relative to the car, right? So what is the speed of the runner? Well, it is 5 meters per second, right? What's the speed of the car, or Carlos, relative to the ground? Well, he's traveling at 15 meters per second relative to the ground. So that's what, 15? So 5 minus 15 is negative 10. So, the speed or the relative velocity or whatnot of the runner, respecting how fast Carlos is going, is negative 10 meters per second. What that basically means is that Carlos is traveling negative 10 meters or 10 meters per second slower than the Carlos, right? Right. So now we're going to tie that back into the idea of relative motion in 2D, right? So you can obviously see here that this is a shortcut for visualizing the resultant vector for subtraction, right? So point A points from head of the second equation to the head of the first one equation, right? So right now we have a vector BG, which is this one right here. So this is the vector of an object B relative to the ground, right? So this is a ground, and this right here is the vector of object A relative to the ground, right? But remember, in order to find, the relative motion of object B in relationship to A, right? You would want to start your arrow at the end of, in this case, vector A in respect of G, and then draw until the head of the arrow is touching the head of the arrow of the vector of object B in relationship to the ground, right? And remember, if you don't remember how to subtract vectors, there is, I believe it's the first video that I've done on how to do this. So check that out. And of course, we got this idea right here, is that the mouse, right? The mouse is trying to get the cheese, right? Right? So he's traveling at 4 meters per second in relationship to the ground, right? Right? Yeah? Okay. So if that's the case, then straight what's the relative factor 4, right? So what is, and now that's the thing, what is the speed of the mouse relative to the floor, right? Well, in any problem that you're given, you want to write the formula out, which is basically that the speed of the mouse, right? The speed of the mouse relative to the ground. So Vm relative to the ground, G, is 4 meters per second, right? Right? And what about 3? 3 meters per second. What is that? That is the speed at which the conveyor belt is moving in relative to the ground, right? If you were to just stand still and just watch the conveyor belt move, you would see that conveyor belt is moving 3 meters per second, right? So the velocity of the conveyor belt relative to the ground is 3 meters per second, right? So what does that tell us? Well, you can see here that the mouse is going to the right and the conveyor belt is going down to the left, right? So that kind of technically forms a triangle, because there's obviously many ways that you can solve relative motion. You either do it two-dimensionally or you can do it formula way, right? In this case, I believe that just sketching it out is going to be an easier way to do it. So let's start with that. So if the mouse is traveling to the right at 4 meters per second, right? Okay, check. Okay, so now what? Well, we would have to draw the next one, which is basically the conveyor belt's vector, right? Well, what is that? That is straight down, right? So, bam. And to be fairly honest, we kind of have a right triangle, right? The 3 and the 4, and you can see here how it kind of hints at us that there's a perpendicular triangle. As mouse goes right, the conveyor belt goes down. You can kind of see it. And once you connect the idea that mouse is going here, the conveyor belt is going down here, what you want to do is you have to determine where the arrow stems from, right? Where is the arrow stemming from? And it's in this case that the arrow is stemming from the mouse, because you're trying to find the mouse's speed relative to the factor floor, right? And it's because of that relativity that you want to stem your arrow, right? You want to start your arrow where the mouse is moving, right? And from there, you actually get the triangle that and the question was trying to hint at you, right? A 4, 3, it's a Pythagorean theorem rule. That's right, it is 5, right? And you can actually see the explanation right here. The mouse, right? The velocity of the mouse relative to the floor is 4, right? And the velocity of the mouse relative to the conveyor belt, right? That's what we're trying to solve for, right? And the velocity of the belt is 3. So you can see here that not only is the green arrow for each corresponding vector shown in the diagram matches with this, but it also shows us that this equation right here, this relative velocity equation, matches with what I discussed, what we presented a couple of slides back, right? And again, notice here that the arrow stems from the mouse, right? It stems from the mouse because we are interested in the motion of the mouse relative to the vector floor, right? And same thing right here, right? So we have what was the bird's airspeed? Its launch relative to the air. It's sure flight speed, right? So we basically have, a bird that's traveling at a velocity in relationship to the wind, right? And the velocity of air in relationship to the wind, right? Right? So what does that tell us? Well, we're trying to find out what is the velocity of the bird relative to A, right? Relative to the air, right? So now let's figure that out, right? So remember our formula where a velocity equals to b of A, right? Velocity of an object B in relationship to A equals to the velocity of object B in relationship to the ground minus velocity of object A in relation to the ground, right? In this case, there is no ground. Our ground or our frame is, in this case, the wind, right? The wind is what connects both the bird's motion, or well, not connect, but like just establishes the bird's motion and the air's motion, right? But what we're looking here is the bird's motion in relationship to the motion of the air, right? So this is how I would set it up. Well, the velocity of the bird in relationship to the air, right, would equal to the velocity of the bird relative to the wind, right? Not the ground, the wind. The wind is the thing that grounds us or defines our, actual speed, right? Minus the velocity of the air in relationship to the wind. And it's the same idea as to why we include the wind there, right? And now we just basically substitute 35 meters per second minus 23 meters per second. Right? And that's 12. And that should be 12. There it is. 12 meters per second, right? Because remember, it's the idea that we follow this formula right here, right? Again, it seems very complicated, but it's really not. And if you are struggling with it, I encourage you to watch every single race and focus on just two runners. You would understand the idea of relative motion and relative velocity once you compare how fast, which is basically corresponding with velocity, or how further or how far away from each other, which is displacement, they are in relationship to each other, right? Right, and that is that example. I think that's the last one. Oh, yes. So again, there's the idea of acceleration also. So remember, it's the same frame. The acceleration of object B in relationship to A is equal to the acceleration of B relative to the ground minus the acceleration of G relative to the ground. Now, of course, I feel like acceleration is a little, I wouldn't say hard, but a little bit to wrap your head around, because you would have to basically tell me how fast or how drastic there are speeding or slowing down, right? So a classic example of what I would say is that imagine that you're a runner, right? Again, I'm using the runner scenario, and you're about to start running, right? And at every start of a race, a runner must accelerate, right? Oh my God, that rhymed. But for real, every runner will gradually build up speed until they reach the maximum speed, right? And it's because of that they have an acceleration, right? They are speeding up, right? That's a clear indication that there is an acceleration on that object, right? That's runner one. But let's say runner two, he does accelerate, but he speeds up slower, if that makes sense. He doesn't speed up really quickly. He speeds up very tiny, right? I don't know if that makes sense, but it's kind of like he's gradually building up speed while runner one he's like already building up speed, right? It's this difference of how much speed you can increase, right? It's a difference in the rate of how fast you can build up speed. One runner is already building so fast speed, right? He's already speeding up so much versus a runner that is speeding up very gradually, right? And it's that idea of relative acceleration. Again, it is very hard to like picture in your head because you don't necessarily think of the acceleration other than the idea of just speeding up and slowing down. But again, if I were to take something out of this lesson, it's this. Relative motion. Relative motion describes the motion of an object in relationship to another object, right? And where are you going to find this more common and frequent? Actually, anywhere, because remember, it only depends on two objects in this case, right? But the most prominent, very, you can visually see that difference is in a race. For displacement, you can see how far away the runners are from each other. In a velocity, you can see how faster or slower they are from each other. And then for acceleration, you can see how much they are increasing speed from each other. One runner is increasing speed faster than the other one. And that's what we're measuring. We're measuring that difference. We're measuring that difference for acceleration. We're measuring that difference for velocity. We're even measuring the difference for displacement, right? And again, it's the idea that the more that you practice with this, the more you get proficient about thinking conceptually about this idea and applying it towards problems and FRQs. So that is our lesson today, and hope that, despite that relative motion sounds like it's a very complicated thing, it's not. And I can assure you that, again, it's just that one watch of a video of runners running. Like, you know what? Just watch the Olympics. Like, literally just watch the Olympics and the part where the contestant starts to do, I believe it's like a specific dash race. It's a specific meter run. I don't watch sports, but watch how they differ in motion and see how you can actually describe that difference using relative motion. Okay, and that is it for today. I hope you guys are doing well, especially during this week. I know that this week is very God, it's so stressful, but you got this. Okay, even though it seemed like you're being handed so much material, you got this. Okay? I believe in you.